Let's continue discussing our power series representations by Taylor series. So we are going to work with a few more questions that are asking us to first represent a function with its associated power series representation. So we have this list of useful power series that we should know, and this is the reference sheet that I've given you in the Canvas modules. Now, we also know from the textbook, we've got a few more power series representations. We've got these ones listed here, and these in the book include some of the hyperbolics, cosh and sinh. So we can use any of these power series representations now that we've derived them, either through the videos in the book, in the homework on the worksheets. We've derived these and their associated radiuses of convergence. And so we can use these to answer follow-up questions, to work with functions, use their power series representations to do things like take derivatives and integrals. And that's what we're going to look at on this video. So for all of these examples, we want to work with Taylor series, and we can use the known series, the Taylor and Maclaurin series that have already been derived, and I reference them as our useful power series, the ones I just had projected on the screen. So for example, like in this first problem, I want to find a power series representation for the derivative of the given function, f prime of x, and find the radius and associated interval of convergence. So we take a function, f of x, which is equal to sine of x squared. And so here is an example of where we know that sine of x has a power series representation. And its power series representation holds for all x. It has a radius of convergence of infinity. So what we're going to do here is we're going to start by representing the function that we have with its power series representation, and then we can take the derivative. So f of x equals the sine of x squared. And I just pulled this little recall. I just pulled that right off of the table we had projected at the beginning. It's one that we derived in class. So we are taking x squared and substituting that into the sine of x's power series expansion. So this goes from k equals 0 to infinity, negative 1 to the k. We're plugging in x squared to the 2k plus 1, and that is all over 2k plus 1 factorial. Now I'm going to simplify that a little bit before I take the derivative. So that goes from k equals 0 to infinity, negative 1 to the k, x to the, let's use rules of exponents there, 4k plus 2 all over 2k plus 1 factorial. Now that is true for all x. So as long as x is less than infinity, or a better way to actually say that is to say it has a radius of convergence of infinity and an interval of convergence from negative infinity to infinity. So this is true for all x's, and that will hold true when I take its derivative and its integral. In this case, we just want its derivative. So now let's go ahead. We now have the power series representation. Now let's go ahead and do a little simplification. Actually, we already got it simplified. Just take its derivative. So the derivative of this function, which is what we were asked to find, would be, let's just think about that. Just taking derivatives, that would be 2x times the cosine of x squared, because I have to use the chain rule there. So the derivative of sine is cosine, and then the derivative of the inner function is 2x. So we're coming up with a power series representation for the function 2x times the cosine of x squared. So now let's take a look at the simplified version of the power series and take the derivative term by term of that guy. Let's take the derivative of the power series from k equals 0 to infinity, negative 1 to the k, x to the 4, k plus 2, all over 2k plus 1 factorial. Now, when we take the derivative, we can literally take the derivative, bring that derivative symbol inside, and take the derivative. Remember that these factors right here are just constants, so those will stay the same, and we're taking the derivative of x to the 4k plus 2. That represents the powers on x. So we end up with negative 1 to the k. We end up, when we take the derivative, applying the power rule, we get 4k plus 2 times x to the 4k plus 2 minus 1, so that becomes 4k plus 1, and that is still all over 2k plus 1 factorial. Now, That is our power series representation for the derivative, and that is going to hold true for a radius of convergence of infinity and an interval of convergence from negative infinity to infinity, because when we differentiate and integrate a power series, its radius of convergence stays the same. But we could leave it just like that. But I do notice there is a little bit of simplification that we could do. So I'm looking right here at this 4k plus 2, and I'm seeing that we could actually factor a 2 out of that, and that would leave me with a 2k plus 1, which in the bottom 2k plus 1 is factorial is 2k plus 1 times 2k factorial. And we might want to simplify that a little bit. And so this becomes k, that's just a common factor that we could clean up a little bit. Negative 1 to the k, then the 2k plus 1s would cancel, so we'd have just 2 times x to the 4k plus 1. Now in the bottom, all that's left is 2k factorial, and we could leave it in that form, and that does make things just a little bit nicer. So that was my derivative of that function sine of x squared. That's the power series representation. And if we wanted to, we could start writing out terms. I think I'll leave that. We did a lot of that on the last video. We could start writing out the non-zero terms if we wanted to, just plugging in our index from k equals 0 to 1 to 2 to 3 and go as far as we needed to. So that is how we could take a power series representation of a function and then use it to find the derivative of that function. Okay, let's do some integration. So for these next two problems, I actually want to approximate the following using a Taylor series. So I'm going to come up with a Taylor series for a definite integral, and then I'm going to find that value to within an error that is less than 10 to the negative fourth, or 1/10,000th. So we want to actually not just evaluate the integral, but evaluate the definite integral, which will give us a numeric power series, and then we're going to approximate this value right here, because we know that a definite integral is a number. It represents a number, a value, and so we want to approximate this value to within the actual value, because this is going to be an approximation, so to within the actual value where the error is going to be less than 1 over 10 to the fourth, 1 over 10,000. So how are we going to do that? Well, we're going to start by representing this function here, sine of x squared, with a power series. So let's start with that. It's actually the same function we looked at before when we were differentiating, but let's just redo it. So again, recalling our formula for the sine of x, and we're going to plug in x squared for x. So we're going to get the power series, excuse me, k equals 0 to infinity, negative 1 to the k, x squared to the 2k plus 1, all over 2k plus 1 factorial. And we do have to integrate that. We're integrating it from 0 to 0.2. We'll do that in a second. Let's get this cleaned up first. So you know what I actually am going to do? Because I want to work with, rather than decimals, I prefer to work with fractions. So this is 2/10, which is 1/5. So I'm going to write that as 1/5. Okay, this is the power series from k equals 0 to infinity and negative 1 to the k. Use my rules of exponents there, and that becomes 4k plus 2 all over 2k plus 1 factorial. And we want to integrate that. So just like with derivatives, with power series, we can just integrate term by term. So this whole piece here is a constant. That's the constant, the coefficients on each of the terms in the power series. So when I'm integrating each of the terms, applying the power rule to the x to the powers. So we're going to end up with, when we integrate, we're going to get a power series. Now we do have to evaluate this power series from 0 to 1/5, so we'll do that in a second. But what is the power series when I integrate term by term? Well, we still have the negative 1 to the k. When we integrate x to the 4k plus 2, the rule of power says that we increase the power by 1, so that becomes 4k plus 3. And we divide by 4k plus 3, and we still had the 2k plus 1, the constant, for each term was still left in the denominator. So we still have that hanging out in the denominator. Now, we're going to evaluate that power series. We're going to plug in x equals 1/5 and x equals 0, and we're going to see what we get. So when we plug that in, this definite integral becomes the power series k equals 0 of negative 1 to the k, 1/5 to the 4k plus 3 all over 4k plus 3 times 2k plus 1 factorial minus, well, when I plug in 0, I just get the power series of 0. So that whole thing becomes 0. We're just subtracting 0. So this definite integral that I'm looking at has boiled down to the power series from k equals 0 to infinity of -1 to the k. Now the 1/5 to the 4k plus 3, I'm going to actually move that over just a little bit, is going to drop to the denominator as 5 to the 4k plus 3 times 4k plus 3 with all the other constants that are in the denominator, 2k plus 1 factorial. So I just dropped that 1/5. I dropped the, 1 to the 4k plus 3 is just 1, so technically there's a 1 in the numerator, and I dropped the 5 to the denominator. Okay, so that's what my definite integral is equal to. Now remember that this is an infinite polynomial. Actually, it's alternating in signs, plus, minus, plus, minus. This is an infinite, it's not even a polynomial, it's actually an infinite series. It's numeric now that we've plugged in the bounds. So if I want, remember the goal here was to approximate this Taylor series so that the error was less than 1 over 10 to the 5th. Well, let's start writing out a couple of terms and see what this guy looks like. One thing I want you to notice right from the get-go is that we actually have an alternating series. And way back in the alternating series section, we had the alternating series estimation. When we did estimations with the alternating series, we said that the error is always less than or equal to b sub k plus 1 if we've used, actually let's say n plus 1. If we use the nth partial sum to estimate, to approximate the actual sum, then the error was always less than the n plus 1 term. So what's super useful about that, I'll circle this as a little recall as well. Recall. What's super convenient about alternating series is if we want to use n terms to estimate the actual sum, so we're trying to estimate right here, we're going to do a little approximation. We want to estimate. If we have an alternating series, all we have to do is go until we see a term that is less than the error that we want. In this case, we want the error to be less than 1 over 10 to the 4th. So let's write out a few terms and see what we end up with. So when k is, let's see, we start this series at 0, so let's do k equals 0, k equals 1, k equals 2. I don't know how far we have to go out, but let's see. Let's see how far we need to actually go out, and we'll estimate this. You know, I'm going to move my recall real quick. Okay, so let's keep going. So k equals 0. So when k equals 0, we have a positive 1 over, now when we plug in the bottom, we end up with 5 cubed times 3 times 1 factorial. Then we get minus 1 over, when we plug in 1, we get 5 to the 7th times 7 times 3 factorial. And then when we go to the k equals 2 term, we get a positive, it's alternating series, so we get a positive 1, 5 to the denominator. Notice real quick, as I'm doing this, I'm just kind of looking at that. Notice how quickly those denominators are expanding. Watch this one. We're going to end up with 5 to the 11th. That is a very big number already before I even multiply by 11 and then multiply by 5 factorial. These are getting, the denominators of these terms are getting really, really big. These terms get small because it's just 1 divided by that denominator. These terms themselves get small really, really fast. Okay, so let's write out what each of these, because it's, you know, when they're in this multiplied, this factored form, it's a little hard to actually see what these numbers are. So let's write it out. So this is 1 over, I just grabbed my calculator, plugged these in, and I got 1 over 375 for the first term, the 0th term, and then for k equals 1, the actual second term, I got 1 over, look at how quick this became big, 3,281,000, I have to look at my notes, 250. I'm not even going to go any further because right there, notice that by that first term, that term, if we just took this value, if that was our approximation, if we just took the first term, which is the 0th term in our notation because we let k start at 0, notice that the error in using just one term, just using the a sub 0 term, the error in using just one term is less than the absolute value of 1 over 3281250, which is clearly, you can just see that bottom, that is less than 1 over 10,000. That has to be, the denominator is so much bigger. That is definitely, so it's so like, this is so mind-blowing, right? Like we only had to use one term. We only had to use one term to get what we wanted. So we only need to use one term to estimate this value. One term of an infinite number of terms. We only need to use one term to estimate the value of this integral. So we only, the value of this integral, I should say this, the value of this integral to within 1 over 10 to the fourth. That's what we're saying right there, that we only need to use one term to estimate this to within 1 over 10,000th, 1 over 10,000 of the actual value. So in fact, the value of this particular integral can be approximated if we go all the way back to where we started right there. The value of this integral from 0 to 0.2 sine of x squared dx is approximately 1 over 375. And that is within 1/10,000th of the actual value. And we can see that just using, we're putting together a lot of pieces here. We're putting together our, known power series for the sine of x, we're integrating it, we're plugging in values, and then we're going back and we're calling the alternating series estimations. And the alternating series estimations, it's the easiest of our estimation theorems because it says that if you use the first n terms, then your error has to be less than the next term from where you stopped. So if we stopped after just right there, we stopped after just the first term, then the error has to be less than the absolute value of that next term. So we literally only had to use one term to get this estimation. Okay, let's take a look at another one. Okay, on this one, we are using a binomial series because this integral, I'm going to come down here where I have more space. This integral from 0 to, and again, I prefer to work with the fractions rather than the decimal. So I'm going to go from 0 to 0.5, of course, is 5/10, which is 1/2. So I'm going to replace that 0.5 with 1/2. This is actually 1 plus x to the 6th to the minus 1/2 dx. And so that fits right into our binomial series where p is negative 1/2. So I reference this here. And this was not relevant actually so much on the last one because the last power series that we used had a radius of convergence of infinity, so we could have plugged in any x's into our integral. But in this particular case, the absolute value of x has to be less than 1, and so we, of course, can only use a power series representation if the x's we're working with are within that radius of convergence. So that is true in this case, but we would want to clarify that. This is integral from 0 to 1/2. So we're going to take this guy and we're going to represent it as a power series. And then we're going to integrate it and we're going to plug in the values and we're going to estimate it to within 1 over 10 to the fourth. Same instructions as the previous example. So this can be represented as a power series from k equals 0 to infinity of negative 1/2, choose k. Now, in this case, the x that we're plugging in is x to the 6th. So this is x to the 6th to the k. And we're going to integrate that from 0 to 1/2. So let's get this guy simplified a little bit. This is, before we integrate, 0 to 1/2. This is the power series of negative 1/2, choose k. So up above, right there in the upper corner, I have it written out. So let's start writing out, what does this guy, this negative 1/2, choose k, what does that look like when we start expanding it out using its expansion? So that would be minus 1/2. Then we subtract 1, so it's minus 3/2. minus 5 halves, all the way out until we get to minus 1 half minus k plus 1, all over k factorial and x to the times x to the 6k. Now we are going to integrate that, and when we integrate it, we're going to be integrating just that first. All of this is a constant, so when we integrate it, we're just going to be integrating the x to the 6k. But we'll do that in just a second, and then we'll plug in the bounds. I just want to clean this up a little bit and play with the binomial series here for a minute. Now, for k equals 0 to infinity, I look at this and I'm thinking, you know what? Let's look at this numerator. I just really don't want to write this numerator as it is. So by the way, this is minus k plus 1 half to start. And then I look at that and I see that I could factor out a negative 1 from all of those terms. So that's what I'm going to do. I'm going to factor a negative 1 and that will leave me with 1 half, positive 1 half, positive 3 halves, positive 5 halves. This term here, when I pull out a negative, will become k minus 1 half when I pull out the negative. Excuse me. But I notice that there's a 1 half in all of those factors as well. So if I pull out a 1 half, I get 1 half to the k, and that leaves me with 1 times 3 times 5 all the way out until I get to, now I pulled a 1 half out of this k minus 1 half, so I get a 2k minus 1. And that is kind of a nice little simplification that we can then work with. Because again, remember, after we integrate, we're going to be plugging in some values. And so that gives me a nice little simplification to work with. This dx is over here. Maybe we'll put our power series in parentheses. We still have to integrate. We haven't integrated yet. Okay, now what I want to mention is that this rule, we do have to be a little bit careful. This rule right here that I've just generated, so I generated by doing all kinds of kind of fun factoring and pulling things out, cleaning things up really nicely. This rule is not going to hold when k equals 0. So when we do this, when we're doing these algebra, sometimes we have to pull out maybe the first term or the first couple of terms if we're going to be doing this kind of simplification to work things out. I just noticed that I wrote 2x minus 1. That should have been a k. 2k minus 1. I think I was looking ahead and thinking about my x factor next. So what we need to do here with this little star is we need to pull off the k equals 0 term. So I'm going to go ahead and do that. Let's pull off the k equals 0 term, and then we can integrate this. Okay, so I just rewrote that where we pulled off that k equals 0 term because it didn't match the pattern that we had derived when we factored out that negative 1 and that 1 half. So I pulled that off. Here's our term when k equals 0, negative 1 half, choose 0, x to the 0, which of course is just 1. So we're going to be integrating from 0 to 1 half. We have 1 plus, now we have this whole term. Now I did do a little bit of simplification on that one. I pulled that 1 half to the k from above, and I brought that down as 2 to the k in the denominator along with the k factorial. And so we're going to be integrating that whole term. I am not going to rewrite that. We'll just go right into the integration. So we're going to integrate. The first term that didn't meet that pattern was that constant 1. So when we integrate, that becomes x. Then we're going to have the series. We're going to go ahead and integrate that series from k equals 1 to infinity. We have those constants, and they're kind of, arithmetically, they have quite a bit going on, but let's just go ahead and carry that constant down. So it's negative 1 to the k, 1 times 3 times 5 out to 2k minus 1. Now remember, that pattern worked as long as k started at 1 for the coefficients. We have a 2 to the k in the denominator times k factorial. And then we need to integrate the x to the 6k. So we're going to integrate that, increase the power by 1, x to the 6k plus 1, and divide by 6k plus 1. And I'll put that in parentheses since there's some other factors in the denominator. Now it's a definite integral, and we're evaluating it from 0 to 1 half. So this, again, remember, is representing a infinite polynomial in here. We're going to evaluate it from 1 half to 0, or 0 to 1 half. Apply the fundamental theorem. So what we're going to get, we're going to plug that in. We're going to get 1 half plus the series from k equals 1 to infinity,
negative 1 to the k times that pattern, 1 times 3 times 5. Almost a factorial, but it is not because the factors are going up by 2's in that case, the odd numbers. We're going to plug in 1/2. I'll put the denominator in just a second. For x's, we're going to plug in 1/2 to the 6k plus 1. And in the denominator of each of the coefficients, we've got a 2 to the k, a k factorial, and 6k plus 1. And then we're going to subtract from that when we plug in. So all of that was plugging in, applying the fundamental theorem of calculus. We just plugged in 1/2 minus, and then we've got to plug in 0. So when we plug in 0, we get, I guess let's put this all in parentheses. When we plug in 0, we get 0 for x plus, and then we have the summation of 0, which of course all of that is just 0. All right, so let's come back down here, and there's not a whole lot more to simplify. So let's actually start writing out a couple of these terms. So this is 1/2, and then when k equals 1, let's write out a few terms. We're trying to estimate this to within 4 decimal places, I believe. Let's grab that from above. Okay, so I just had to, we've gotten going on this problem and I forgot. We wanted our error to be less than 10 to the negative 4th, or we want the actual estimation we're going to get here for this definite integral. We want it to be within 1/10,000th of the actual sum, the actual value of this integral. So let's go out. This is going to be an alternating series, which is convenient. So we can use our alternating series estimation. And so remember, with the alternating series estimation, we know that we are looking for, or that the error is just simply equal to the first term, the error in using, let's write n, the error in using s sub n as an estimate is simply less than or equal to the n plus 1 term, the first term, the absolute value of the first term that we leave off. So that makes it really nice, because what we can do is we can just start adding up terms, and we can see when our error is going to be less than. So we want to stop right before we get to a term that is less than 1/10,000. So let's see. I don't think, looking at this denominator right here, I think these, and plus we've got 2 to the 6k 1/2, but we also have in the denominator a 2 to the 6k plus 1. So these terms are going to grow incredibly fast, incredibly quickly in the denominator. So let's get in here and let's start writing out a couple terms. I don't think we're going to have to go very far, is what I wanted to say, but I had to grab the actual error that we were looking for there. So the k equals 1 term is actually going to be negative. So it's going to be negative on the top. When we plug in k equals 1, we're going to get 1. In the bottom, we get 2 to the first times 1 to the first times 7 times, and we have 1/2 to the 7th. So that's actually going to be a negative 1 in the top, 2 factorial, sorry, not 2 factorial, 2 to the first, I'm not going to even write 2 to the first, times 1 factorial, which is just 1, times 7 times 2 to the 7th. All of that in the bottom. The k equals 2 term, the second index, that guy's going to be positive. And in the top, we're going to have 1 times 3. We'll have those 2 factors in the top. In the bottom, we're going to have 2 to the second times 2 factorial times 13, all times 1/2 to the 13th. I'm going to stop there for just a second. I'm going to carry a couple more terms down. I'm going to grab my calculator, because I think this term might be enough to get us where we need to be. So we have 1 times 3 in the numerator, which of course is just 3. In the denominator, we've got a 2 squared, a 2 factorial, a 13 times 13, and a 2 to the 13th power when we distribute that exponent to the numerator and denominator of the 1/2. Okay, so I grabbed my calculator. Let's see what we got. So 1/2, the denominator of the first term is 1792. The denominator of the k equals 2 term, technically our third term here, is 851 968, 851,968. And I can stop actually right there because this term right here is less than 1 over 10,000. I can see that's less than 1 over 10,000. We could look at it in its decimal expansion. As a decimal, this is 0.1, 2, 3, 4, 5, 3, 5, 2. We don't need any more decimal places, but it is definitely giving me more decimals of accuracy than I need right there. So we wanted to get to a place where we had a term that was less than 1 over 10,000, 10 to the negative fourth. So we're within 4 decimal places of accuracy. And what that's telling me is that I only needed the first 2 terms. Since we started our index at 0, that's the 0th term and the first term. If I add up those first 2 terms, so S1, which is 1/2 minus 1 over 1792, then the error by the alternating series estimation theorem, the error will have to be less than or equal to the B sub 2 term in absolute value. So my error is less than or equal to 3 over 851,968, which is less than 1 over 10,000. It's definitely less than. So all I had to do was add up the first 2 terms. So we didn't even have to go very far to get within 4 decimals of accuracy. So S1, if I plug that into my calculator, I actually get 895 over, I have to look at my calculator real quick, 1,792, which is approximately 0.499. And that sum estimates the actual sum to within 4 decimal places. So it's actually even better. It's we could say the error is less than 3 over 851,968, but it's definitely giving me at least 4 decimals of accuracy because it's less than 1 over 10,000. The error is less than 1 over 10,000. Okay. So that was, and that one I wanted to show you just how to simplify that binomial. I'm trying to get it all on the board there. I also wanted to just show you how to simplify that binomial with the fraction like we did up. Oh, I have to go even further. Like we did up here where we took that 1/2. We took that P choose K, taking the power that was on the binomial there, and choose K, and we simplified it. We had a fractional power, fractional exponent, so we had fractions in the expansion, and we simplified that out, and we got it down to this expression that's almost like a factorial, but not really. So almost like a factorial, but not really, because the factors are going down by 2s each time. We can pull out that first term in the expansion, the power series expansion, because it doesn't fit the pattern, but after that, it all fit the pattern. So it's kind of nice. Technically, you didn't actually have to do that. We could have left it up here. We could have stayed at this level and just expanded, or even at this level, just started looking at individual terms, just like we did, because we didn't have to go very far. So maybe not having the pattern was okay. But I wanted to show you how to come up with that pattern here, generate that pattern.